Sorry, now I am. So as you go down, you increase principal quantum number or you increase your size. That's basically just a fancy way of saying you're increasing your size. So if you're increasing the size of your atom, you have more space to accommodate those negative electrons, that negative, formal charge. So again, our trend here is the less electronegative, the more stable, okay? The less electronegative, the more stable. So let's kind of go back here and rank these, okay? So if bromine is the least electronegative, it's the most stable, okay? Then chlorine would be next, and then fluorine. Okay, so let's kind of rationalize that again. So if I had a reaction, let's just say, this is the logic here. And this could be how it's presented on your test, right? So, okay, so this is me giving you like a problem. Ready? So I could be like, given the above, reaction scheme, so given this, what would happen to the reaction rate? So my question is, what would happen to the reaction rate if A, I change the halide to fluorine, and B, if I change that halide to chlorine, okay? Does the reaction rate, ready, increase or decrease? Does the rate increase or decrease? And this is a very classic type of problem that Dr. Peterson and Habenecht are gonna ask you on this test, okay? So let's just look at A. So if I go from bromine to fluorine, that fluorine is now less stable in terms of its leaving group ability. So my rate goes down, okay? You guys kind of following how we can predict all this stuff? With the chlorine one, if we put chlorine, the rate also goes down. Well, I shouldn't have picked bromine. I should have picked, something else, like probably something intermediate. But essentially, you can rationalize that leaving group is going to dictate how fast these reactions progress. And that's a really important connection you have to make. Cool. And we just assumed SN2 conditions. Okay, so SN2. Anyway, so that was A. So let's kind of look at B. So for B, we have a different example. So it looks like we have hydroxide. Okay. It looks like we have some sort of carboxylate, anion, and we just have plain water. Okay, so let's think about these again. So remember, leaving group ability. Okay, so the first thing I think I told you guys, and remember, I'm just gonna say one word, and hopefully this helps you guys, lightning, okay? For you guys that have always been with me since the start, does lightning ring any bells to you guys? Okay, remember that analogy with charges? Yes, great, Abby, you got me. Okay, it's okay. So Abby, you got it. So charge, yeah. So remember, charged things are not good. Nature hates charges. That's why lightning is a thing. That's kind of a big theme in organic chemistry. We don't like charged compounds. So anytime I see a neutral compound, it's out of this kind of series of molecules, I'm instantly gonna say that this neutral compound leaving the molecule is so good because look, once it leaves, there's no charges. It's stable, it's happy the way that it is. But when these leave, they're charged, so they're not as happy, okay? So that clearly gives me this is the best leaving group. But then now I have to think about these two. And again, it goes back to trends we've already seen. So with this carboxylate versus this hydroxide, what's a stabilizing feature I see in this carboxylate that's not present there? Okay, in the chat box, what do we think? Resonance, great, resonance, you guys got that. So resonance stabilizes or destabilizes? Stabilizes, great. So the charge spreads out more. We have kind of this resonance kind of situation going on. So we get this alternating, contributing structure. I know it looks the same, but essentially we're spreading that charge. So this is pretty good. We're stabilizing this molecule more. And here we don't have resonance. So that's kind of the situation. And again, let's do this kind of example. So let's just say let's just do a tertiary example. So I have this. I have, okay, and I'm going to subject that to, let's just say, ethanol, and yeah, that's it. And essentially, I'm going to say, okay, if I change that leaving group, I'm going to call it X just for now. If I change that leaving group to the hydroxide, does the rate increase or decrease? And B, if I change the thing to leaving group to water, so H2O, does my rate increase or decrease? And again, I like doing this because this is how you have to think, okay? So first of all, what type of reaction is this? SN1 or SN2? I'm gonna wait for more people just to see what's the consensus. Okay, yeah, SN1, right? So this is definitely SN1, we're a tertiary starting material. So the rate is dependent on this leaving group leaving, right? This rate just depends on that whole thing leaving on its own. Okay, so for A, if I were to change that leaving group to hydroxide, so a worse leaving group, what happens to the rate? Increase or decrease? Decrease. Great. Okay. If I change the leaving group to water, a better leaving group, does it increase or decrease the rate? Increase. Great. Awesome. Okay, you guys got it. Cool. All right, so that's A and B. Are you guys doing okay so far? Somebody let me know so you guys aren't freaking out. Good. All right. Let's do one more. Let's do C. Okay, so again, we have this example. So we have NH2 charged, NH3 neutral, and HN. Okay, so there's amide. Okay, again, I think this is pretty obvious, right? So what did I just say? Which one's the most stable immediately? What do you think? Ammonia. Great, so 3. Okay, then out of the amine versus the amide, which one's better? Amide. Great. 2, 1. You guys got it. Awesome. So just being able to do that, it's really easy. You know your stabilizing trends at this point. And as long as you know this concept, this main concept that, you know, the rate is dependent upon this stability of that leaving group. Okay, so that's kind of a really, really big trend. I'll write that up top. Rate and this alpha symbol, you guys will start, you know, seeing a lot as you progress through science. That means directly related to leaving group stability. Okay, so what this kind of abbreviated thing says is the rate of this reaction is directly related to the leaving group of the stability. Excuse me, the stability of the leaving group. There you go. Okay. Yes, and because of resonance. That's right, Lauren. Okay. I think that's good. So let's kind of move on. So we can have different types of ranking questions now where we talk about the nucleophile strength, okay? And when you have these questions, okay, so if you're sleeping, wake up for this, this is important. These questions are dependent on the solvent, okay? So if we were to say, assume, you know, acetone is the solvent, what reaction conditions does that tell me? Let's say acetone, what does that tell me? SN2, right? But let's say my solution is ethanol. What pathway is that if it's ethanol? SN1, right? So I think it's kind of important because I don't answer your questions on Piazza, but I definitely see them a lot to kind of see where you guys are at. And I think there were a couple of questions today saying, I don't know what polar protic versus polar aprotic is. And I think I talked about that sufficiently last class, but again, just really quickly, polar protic, meaning it has a proton. Polar aprotic, meaning it doesn't have a proton to give. So what are examples of that? Well, water, classic example. Okay, carboxylic acid, you know, something that can give off protons, and alcohol, okay? These all have protons that are acidic, okay? We know why they're acidic at this point. You know, we talked about all that in the beginning of the semester. So all of these, you know, solvents have protons to give. Okay, let's take another example. So this is acetone. Okay, so this is acetone. Okay, this is, this is going to be dimethyl sulfoxide. So this is DMSO. Okay, I'm trying to remember these lower structures from my lab. DMF, dimethyl formamide is, I think it's that. Yes, it's DMF. Again, this is all from my memory, so I don't know if that's necessarily right. But essentially, these are some 3 examples, right? So the difference between the polar protic and the polar aprotic is they're both polar compounds. Like, that's kind of obvious. They're both polar. But the difference is that the protic conditions have protons, and the aprotic conditions, they do have protons, but they're not as acidic as you would like them to be. So what's happening is here, there's no proton transfer to your nucleophile. That's kind of the main key here. And here, there is proton transfer to the main nucleophile, okay? So this is a situation where we would want SN1, okay? And this is a situation where we want SN2. Okay, and we're going to see that in a little bit in more detail. Okay, so are we all clear on the difference between polar protic solvents giving me SN1 pathways, polar aprotic gives me SN2 pathways? And Caroline, yes, I'll get to your question. Okay, good. Okay, so the first question is now, it says, assuming acetone is the solvent. So as soon as you read that, please do this. As soon as you read that, write SN2 on huge letters, big font, whatever you need to do on the test, okay? That's like so important because you get the whole thing backwards if you don't know that it's SN2 or SN1. So clearly, everything in 2 is going to be SN2. So then when we have this first series in A of, you know, nucleophiles, okay? This is really cool. I have another good analogy for you guys. I like this stuff. Okay, and we're actually going to modify this problem according to Dr. Peterson. Again, I wrote this book, so there's sometimes some issues with the questions. So we're going to omit part 3, okay? Omit that last molecule. And if you guys wonder why, it's just because the stability of that molecule is a little bit close to one of the other molecules that we have there. So we're just going to, keep that for simplicity purposes, okay? So essentially, we want to know which one is the strongest nucleophile, okay? So let's think about that. Well, with acetone as the solvent, that means that we don't have protons to give to this. So that makes basically makes all of these nucleophiles as nucleophilic as possible. So there's really nothing we have to consider beyond what we already see, okay? So we don't have to go a step further. We just know that there's no protons being transferred. These are all of our structures. Let's kind of look at the identity of, those negative charges and see if that gives us some kind of logic there. So I hate to use this analogy, especially with like the recent times of, what's happening, what happened with Douglas and stuff like that. So when I say this, I don't mean it in any type of bad way, but nucleophiles really should be thought about as bullets. And why I say that is because these bullets are really tiny and really compact, and they move really fast through space. And kind of that's the logic you want for this nucleophile. And another example I sometimes say is, you're basically a track runner, you're a sprinter, and you're running across your track field, your 100-meter dash, and you need to get to the other end as fast as you can, or to the other molecule, to that starting material as fast as you can, okay? So essentially, you want something small and light, okay? That makes sense, right? You want to be really kind of small framework, and you want to not weigh a lot, okay? And that's how you would run the fastest. So that's the logic I use for these. So the smallest ones would first of all be this one, and this one, just based on pure branching pattern. You see you have an extra methyl group. So these two are definitely the smallest or the lightest. So yeah, I like these two. Okay, so as being kind of very, very good compared to that one. Okay, so 4 is the strongest. So we're just gonna go ahead and still use that numbering scheme. So 4 is my strongest one. So now out of oxygen or sulfur, we know they both are kind of similar in terms of their weight or size because of this branching pattern. But the oxygen is negative versus the sulfur being negative. And remember our trend that, can you see oxygen? Yeah, so oxygen is here. That is more electronegative than sulfur. So in terms of nucleophilicity, let's think about that, logic. The nucleophile wants to give off electrons to something else. This is an electronegative thing that wants to keep its electrons. So sulfur, since it's less electronegative than oxygen, doesn't hold on to its electrons as much as the oxygen, and can therefore be a better nucleophile than this electronegative oxygen, okay? So that should kind of give you some insight into, selecting this as number 4, okay? That's the best one, okay? It's relatively lightweight, and it doesn't hold on to its electrons as great. It wants to give them off. Then here, this one is relatively light, but this is a little bit more electronegative, okay? And then here, this is obviously number 2, because yes, it's more electronegative, but also now it's heavier, okay? So think about now you're a track runner, but you put on one of those weight vests, like that the military uses. So now you have to run with extra weight added on. So it's harder for you to, perform that reaction. Do you like those analogies? Are you guys okay? Is everybody okay with that? Yes, so exactly. Yeah, the bullet thing. Okay, so again, and we're gonna see this example. So I don't know if you guys have ever heard of, have you seen this yet? NaN3 as one of your main reagents yet? This is a really common reagent you'll see in this chapter, NaN3. You see that? Is it familiar? Okay, so N3, this is called, this N3 anion, N3 minus, is called azide. And this is why I'm gonna connect your question right now. Okay, so let's look at this. Okay, so let's look at this structure. Okay, so I'm gonna share my screen. This is important to note. Let's see, how do I share? Sorry, here. So I literally just Google searched azide, okay, an electrostatic map. And if you can look to the right, okay, right over here, you guys can see, oops, you guys can see that, the difference here is between, the amide version, and then this is azide, N3, okay, N3. So you can basically ignore everything to the left. So let me just draw on here. You can ignore, here, where's all this? You can ignore really all of that, and you can ignore all of that. So just look at the kind of the blue spheres, right? So get out of there. So blue spheres. So look at the arrangement of azide. So N3 over here, I'm just going to highlight it. N3 is what we're referring to. N3, actually, I should probably change the color. Let's do yellow. So N3 corresponds to those N3. Notice they're all in a line. All three of those atoms are in a linear trajectory. And look at this electrostatic map. Do you see it looks like a bullet? How it can like pierce through things? Like, what's another example? Look at this one. Yeah, let me clear. So here's another picture. Clear. I hate this thing. Zoom is so bad. Okay, so look at this one. This is azide again. So you can see how, look at that. It looks like a bullet that can pierce through. So now you're kind of making the argument of azide versus, you know, maybe acetamide coming in. You can see that, you know, again, ignoring the acetyl group, you have azide as this kind of tiny compact bullet coming through. Let me see if there's better. Look at this. This is perfect. Look, that's the electrostatic map, basically. Just showing how like red means electrons, blue means positive, so negative, positive. And essentially, look at that. It looks like a bullet, right? Here's another example. We like nucleophiles that look like that, not things that look like that, essentially. We don't want blobs, okay? Do you guys make that? Does that make sense? I don't know. I just quickly Google search these things. So that's the bullet example. You want something tiny, compact, lightweight, yada, 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 yada. Things like that. Okay, let's see. So what's going on in the group chat? I'm confused. Here we go. If we see the solvent as a characteristic parameter, is it 100% safe to assume that it's SN1 respectively, or no? 100% safe to do that. You have to do it. We're not going to trick you any further. Okay, and let's. I'm confused. I thought it's polar A particle because it goes up the group. Goes up the group. No, that's not right, Annalise. So nucleophilicity in aprotic conditions increases down the group because you have less electronegative atoms that bear those, you know, negative charges, which basically means that if it's less electronegative, then you can give off those electrons, and that's what a nucleophile does. Okay, let's see. So for comparing the third and fourth ranking, do you compare the negative and positive charges? No, I'm not comparing anything. The positives are spectators. This has absolutely nothing to do with the answers to the questions. What I'm comparing is, wait, what was the numbers you said again? Let me see. You moved. I think you said, oh, I lost you. Where did that question go? Oh, here we go. Do you compare the negative and positive charges? So no, what I'm comparing is between 3 and 4, the negative on the oxygen versus the negative on the sulfur. That's kind of the main key there. And sulfur is less electronegative. Okay. And yes, it has E1 as well, but that's not going to be necessary, Abby, for these questions. Okay. And Caroline, isn't it longer than the NH2? Yeah, yeah. But what the thing is I wasn't looking directly like NH2 versus, I wasn't doing this. Hold on, and I know you can't see. I wasn't doing NH2 versus N3. I wasn't doing that. I was basically just showing kind of like the map of the blobs, basically. So it wasn't like a legit, you know, thing. Up to the key because it was wrong. Did anyone else see that? What key? For this chapter, you guys talking about? I don't know. Maybe she does. Maybe she won't. I mean, I haven't seen an error so far. Maybe we'll encounter an error in one of the problems, and we can kind of discuss it. So we'll see. All right, so let's keep moving. So for B, let's kind of do another example of that. So we have kind of this ONA, ONA, okay. ONA, and NaOCH3. So here the main difference is we're not really dealing with different heteroatoms, meaning before we had, you know, in this example, oxygens and sulfurs present. Here, everything's consistent across the board with oxygens being the identity of, you know, those negative charges. So for all intents and purposes, I'm just going to rewrite so you guys can rationalize that these are the main nucleophiles without their spectators. Okay, and remember the analogy. Either whatever you want, either like the bullet analogy or the track runner. Okay, now I'm going to give you guys a little bit more insight. So essentially, the negative on the oxygen isn't going to help me, but we know the branching pattern will. So now, building on the track analogy, because I used to run track in high school, like, has anybody ever trained with like a parachute? Like, anybody know what that is? Like, they literally tie a parachute to your back, and when you run, it's supposed to pull you back. Okay, so like, I hope you guys know what I'm talking about. It's a parachute that pulls you back. Yeah, I hated it. So you guys know what I'm talking about. So essentially, like, that's what branching does. That's what this beta branching does. So sorry, I didn't mean to say beta branching. I just meant to say this branching pattern. So as you add substituents, you can basically say, I'm adding more and more parachutes to my back as I'm running. So this is really slowing you down. So imagine like, I'm this guy and I'm trying to run, but like my track coach is really like terrible. And, I don't know, this is me trying to draw some excuse of a parachute, and you're just trying to run forward, but, you constantly are adding weights. So it's, by adding these methyl groups, so it slows you down. So essentially, which one is my best one? It's pretty obvious. 4 over here, this methoxy one. That's like the smallest one. Then 3, then 2, then 1. Boom. All right. How do you guys feel? Smaller the better. That's right. That's what I'm saying. You can rationalize it with the track analogy in real time, but you can also just like kind of always go back to the bullet example. You want small, compact, can travel through space like that. Okay? Yes, Leela, small is better. Lauren, y'all remember when you have someone else sign in the back? Exactly, y'all remember. It's funny. Okay, so C. So essentially, we have this, we have that, we have that, and we have this. So this is a little bit more complicated. Okay, so now that we are assuming, still aprotic, conditions, none of these are really charged negatively except for the protonated amine. Okay, so now remember, we are nucleophiles here. So let's just look at this one. I think this is pretty obvious, right? So for this structure, let's just draw that out in the Lewis form. Does this protonated amine have any electrons to give? No, right. So it doesn't have any electrons to give. So is this even a nucleophile? No. Great. The worst one. You guys got that? So this isn't even a nucleophile because there are no lone pairs to donate into. There's no mechanistic. I can't draw a mechanistic arrow here. So maybe if you're thinking tricks, like anytime you see this like fully protonated, fully protonated nucleophiles are no longer nucleophiles. Okay, because it's protonated. You don't have those lone pairs anymore. Okay, so that's kind of a trick. Now, again, the same logic we're going to use is they have lone pairs. Okay, so we don't have a negative charge that's going to be the source of those electrons, but instead we have these lone pairs that are left on these heteroatoms. And the beta branching, I keep saying that, sorry, the branching pattern is still like all consistent. So really all that's going to come down to is the identity of those atoms. And again, out of oxygen, sulfur, and nitrogen, sulfur is the least electronegative, so the best one. Okay, and then out of oxygen, nitrogen is less electronegative than oxygen. So that's my ranking. Okay, I think this is good for you guys. Are you guys good at this point with how to rank these? Good. All right, keep moving. So now we're going to flip it. Okay, so when you're dealing essentially with SN2 conditions, so something I just want to point out. So if you go back to that last problem 2, whenever you see an aprotic solvent, you have to write SN2. Like, I'm not even going to say like optional. You have to write SN2 on your page. I don't know, on your hand. Actually, don't do that because you might be cheating. So just write it down. It's so important. And once you do that, you can always go back to what you know about the SN2 mechanism. And we said, back to, primary versus secondary versus tertiary, we had, SN2 pathways going on here, and then we had some overlap, and we had SN1 pathways going on over here. So we know that the SN2 pathways prefers sterically unhindered substituents. We know that. So if you go back to the first example I think we did, which was A, this is that same logic. Like, which one is sterically hindered? Well, I mean, bad example. Like, you could always go back to the fact that, let's say this is my nucleophile. I'm just gonna make something up. That, maybe this is a nucleophile versus, maybe this nucleophile. So which one's better? Well, this one is so tiny that it can go near this really, sterically unhindered, substituent. So let's just say the primary is like, oh, that's a bad example. So primary is like that, the X halide over there. So this is a primary halide. So this tiny nucleophile can reach this center, this sterically unhindered center, and break it apart. But now if you were to try to do it with this, it's getting harder and harder, or maybe even something like the tert-butyl version. Now it's like really, really hard, okay? Did you guys kind of see that? So always go back to what you know about these main mechanisms and how they work. You know that you want, really, really light, tiny nucleophile with really, really tiny, unsterically hindered, starting materials. Here, your nucleophile doesn't have to be as tiny and as strong. It could be weaker, and you want more sterically hindered substituents, okay? Are we all kind of following that? And then we'll talk about the overlap. Okay, so for the next problem, we're gonna assume water is the solvent. So immediately on my page, what do I write? SN1, you have to do it. Please do it, okay? So let's kind of rationalize how an SN1 pathway works, and we're gonna rationalize this with 3A. So here and here. Was there a question? Somebody have a question? Madison, do you have a question? Okay. Okay. So Caroline, something interesting about SN1, and everybody should probably pay attention to this. So, and Abby, I'll get your question. So essentially, Caroline, SN1 conditions, and I'm just going to draw it like this. Let's just say it's something, and X is my leaving group. The rate determining step is dependent on that happening. Right. Okay. So to an extent, the nucleophile also wants to be small. Like that's just a given. Like that's the ideal condition. But in SN1 conditions, since the nucleophile is not going to cause the leaving group to leave, right? It leaves on its own in this situation. This is SN1. So since it leaves on its own, the nucleophile doesn't have to be as small as it would have been. And it also, you can say, it doesn't have to be as strong as it would have been, because the rate is not dependent like this. So this would be, this is the rate determining step, and this is SN2 conditions. And let's just say I have a nucleophile. This is why it's SN2, it's bimolecular. So essentially, that's happening, right? So you're dependent on the nucleophile in this situation to kick off the leaving group. So the reality is, you really need your leaving group here because there's so many things that are dependent on this nucleophile. You need it to be as small and, tiny, compact, lightweight, like small, molecular weight, all these different things. That all applies to this condition. Here, you can be, maybe you can be a little bit weaker in terms of your nucleophilicity, okay? Because the nucleophile is not dependent on facilitating that. There's two steps. And then now you would have the nucleophile come in, and then you would have, your nucleophile, okay? So that's kind of the main concept there, Caroline. Are you good with that? Exactly. That's good. Okay, so let's go back to this ranking problem. So essentially, these are all my starting materials. So before, the question was different. The question was ranking the nucleophiles, okay? So we could say, oh, let's rank the following nucleophiles under SN2 condition. We could also say, rank the starting material in SN2 conditions. We could say, rank the nucleophiles in SN1 conditions. We could say, rank the starting material in SN1 conditions, okay? So again, there's 4 different combos. We could ask all different types of combos. So just make sure that, you're aware of that. So here we're assuming that this is SN1 conditions. We said water is the solvent. And essentially, we can just imagine that the rate determining step is all of these, substituents leaving on their own, right? So I'm just going to reproduce, the carbocations that are produced below. So we have a secondary benzylic, we have a plain secondary, we have a primary, forming, and then we have, oops, I think I drew that wrong. It would be a primary, and then we would have benzene again. So this would be tertiary benzylic. Okay, so obviously the rate of the SN1 condition, of the SN1 reaction, is going to be dependent on the stability of our intermediates. So clearly, we know this already. We've done this a million times. Excuse me, the tertiary benzylic is clearly the best, followed by the regular secondary benzylic, followed by the secondary, followed by the primary. And it's that easy. Okay, so you consider carbocation stability. Okay, another way, this question is just another way of saying carbocation stability. Okay. No shifting, we're not doing that. No. Don't even consider it. So Abby, that would be an example of overthinking. I do that too all the time, like especially in chemistry. So like, don't do that. This is just like, what is the carbocation you get? Rank them as such. Yes, I got you. Okay, so cool. So let's do B. So essentially, again, you can kind of imagine it's the same situation going on. We have, and if you guys think I'm going slow on this, like we have so much time to cover all this, like, and you need to spend a lot of time on this. This isn't like something that just comes in a day. Okay, so here we are. Imagine all those leaving. So I'm going to just call this is a secondary, allylic. So I'm going to call it secondary allylic. This would be a primary, this would be a secondary, and this would be a tertiary. right? So let's kind of rank those. So this would be 4, 3, 2, 1, assuming that the secondary allylic is better than the tertiary. Okay, cool. You guys good? Why is that? So again, remember, this was something new that came out this year where Dr. Peterson gave you HIAs or whatever they're called, and those are specific, accurate values of what the energy stability is of all of these. And before we didn't have those when I took this class, or we were taught it for the past 7 semesters. So we just always knew that the lesser substituted resonance form, remember from comparing the tertiary to the secondary, this one has resonance, so this one is better than that one. So that's kind of how we've always done it. And I think if you look at the key, she even wrote a little note there, assume that the secondary allylic, she wouldn't, reproduce the same exact type of problem. She'll make it, consistent for all of you. Okay, so don't worry, yeah. Again, I wrote these, so I just tried my best. All right, let's just last problem. Okay, so you can kind of see that all these themes kind of come back in orgo. That's why I said like it really is cumulative, even though it's like not. Actually, I think she skipped 2, so we're not going to do the molecule 2 in here. Again, for just simplicity purposes to make it all streamlined for you guys. Okay, so again, remember this is dependent on the intermediate stability, so we're going to get carbocations there. So basically, I can just say this is secondary with an inductive effect. Okay, this is going to be secondary, but way too far to resonate. And then this is going to be a tertiary. Again, there's no resonance there. So I think that's enough to rank these. It would be 4, 3, and 2. Okay, great. Lilas, how does SN1 factor into ranking? Isn't it just basically, exactly, that's it. This again, so the point is, this is the exact same thing you've been doing since the beginning of exam 3, like chapter 6, right? It's just another way of asking ranking carbocation stabilities. What's IE? Oh, inductive effect? Yeah, it's bad. So that's why it's the worst one ranked out of all of these. Yep, destabilizing. So essentially, let me do this. So I can give you like an applied question where I'm saying, okay, like I'm trying to produce this medicine, that cures cancer. Wow, go me. And essentially what happens is like I'm saying, I'm in my lab and I have 2 vials in front of me. I have vial A, like someone handed me vial A, somebody handed me vial B, and I want to cure cancer because like, why not? Let's dream big, right? So let's say in A, I have this molecule, and the molecule looks like, let me think, let's say something, well, no, I'm just gonna make something up. And I'm gonna do maybe that, and I'm gonna do, let's just do this. And then maybe in B, I'm going to have, maybe, something similar, that molecule. And I want to say, okay, I know that the pathway in cancer to be cured is definitely going to be an SN1 pathway. It's definitely going to be an SN1 pathway. And I need to, rationalize, oh my God, I'm sorry. Okay, and I'm rationalizing that these molecules are going to go under an SN1 pathway. So which vial should I pick on my desk to cure cancer? Vial A or vial B? Cool. You guys got it. Cool. It has to be adjacent, Alexis. Alexis, I'm sorry, I have to do this. Do you watch Schitt's Creek? Anybody? Anybody? Please? Someone? Yes? Alexis, I hope you do, because like now that I hear your voice, I'm just like hearing it in the way that it's like said on the show. I was David for Halloween, if anybody cares. It was like, I love that show. It's so funny, iconic. Yeah, it's cool. All right, so that's that. All right, so that's enough of ranking. Let's kind of move on to, so I'm gonna leave 4 to you guys. So now this is just kind of the same exact thing. Now we're just ranking the starting materials instead of the nucleophiles for SN2 conditions. And again, this is the steric argument, okay? And also leaving group argument. So you have to consider A, like, what's the identity of all of those leaving groups in these sets of molecules and which one are the most stable? And then from there, you can consider, okay, which one is sterically unhindered, okay? And that's kind of, a good thing. Maybe we'll do one example. So let's just do, 4A. I always do this. I say I'm not going to do it, and then I'm going to do it. So for 4A, we're here. And there, and there. Okay, so essentially the first thing I want to look at is the identity of the leaving group, okay? So the identity of the leaving group is going to be the iodine or the chlorine. So that's the first thing I want to kind of determine. Is iodine or chlorine better? And we've talked about this already. What do you think? Iodine, great. So since this is bigger, less electronegative, it's more stable. So this is clearly going to be like a relatively good, starting material to use because that leaving group can just plug off. Then after you identify the leaving group I would say is probably the most important, right? So I would say a leaving group is the #1 priority. And then after that, you can look at the sterics, okay? So now, based on the sterics, with the chlorine examples, primary, okay, secondary, tertiary. This pi bond is there to confuse you, to think that it's SN1 conditions, okay? Don't be fooled. This has nothing to do with anything here. So essentially, you know that SN2, like sterically unhindered things, okay? So that would just literally be primary, okay? That would be the next probably best one. And then the secondary one, okay? And then this one. So let me just circle. This is a whole bunch of numbers. That's my ranking. All right. Steven, you can just do this on your own. Awesome. Yes, that's me throughout the throughout the whole semester. I feel like you can do this on your own. Let's just do it because I want to make sure you guys know everything. All right. So let's just look at 5. So we can do 5 together. Okay. So let me pull up the question. Okay. So if I can. Oh my God. Zoom is really not user friendly. I don't know if any of you guys TA as well or have other TA sessions. I hate it. Like. All right, let me pull this up. So, I'm also, when is Thanksgiving? Wednesday or Thursday? Anybody know? Thursday? Okay, so like, I'm down to still do office hour. I'm going home today to Boca, but if any of you, I'm like down to do an office hour session on Wednesday from home if I can figure it out. So would you guys be attending that or would you guys all just be on vacation? Oh, okay, okay. Wait, Boca, hi, let's hang out. I see that. That's so funny. That's fun. See you at Palmetto Beach. Okay, so I'm pulling up the questions. One sec, guys. You guys feel pretty good on radical chemistry? A question. That's a question. Do you guys feel okay on that? I think it's not too bad. It's like 3 reactions. Cool. Good is relative. All right, here, let me share the screen. All right, so here we go. So essentially, we want to, this is, something that Dr. Peterson loved when I showed this to her. She was like, wow, this is a good question where you had to decide between pairs. And I can see this being a good point, a good question on your test, especially now that you're online. So between the amine, assume acetone is a solvent, right? So that's SN2. So basically that means that we are already like the most nucleophilic that we can in our flask. So let's just kind of use the trends that we know. So is the negatively charged thing that, wants to, actually, there are multiple different ways that you can rationalize this. For me, I could first think the logic of leaving group ability or neutral ability, yeah. So neutral is clearly a better leaving group than this one would be. So that's kind of how I'm doing it. Just think about leaving groups. If ammonia were to leave the molecule, it's pretty happy. But if this negatively charged thing was to leave the molecule, it's not. So if it doesn't want to be stable on its own, like as its own separate product, NH2 minus, then it's a good nucleophile because it wants to be attached to the molecule. You guys all follow that logic? I'll say it one more time. Between the NH2 minus and the NH3, let's think about leaving groups. If the NH3 left, it's stable, it's happy the way that it is. If the NH2 minus were to leave the molecule, that's not happy because it's charged. So it doesn't want to leave in the first place. It would rather stay attached or attack the molecule. Boom, you got some O's. That's awesome. So the first example, for the first answer, it would be this one, the NH2 minus. It's all just logic and being able to like understand where, like what I'm kind of referring to. Like here, this is really saying which one's a better leaving group, okay? And that better leaving group is going to be the worst nucleophile. Does that make sense? If it leaves better, it doesn't want to attach to the molecule in the first place. Okay, again, fluorine versus bromine. Which one is the better leaving group? Bromine is the better leaving group because it's more stable. So that means that fluorine would be the better nucleophile. Boom. Again, out of these two, alkoxide anions, the difference is not the identity of the atom with the negative charge. They're both oxygen heteroatoms, but the difference is the beta branching, the branching pattern. So essentially, we said the track example, you want to be very lightweight. You don't want to have a lot of, sterically hindered, weight on you. So that's why this one would be the better nucleophile than this one, okay? And then here, another trend, so oxygen versus nitrogen. So the less electronegative thing, we said, was capable of donating its electrons more. remember, the species that holds onto its electrons the most, i.e. this oxygen, keeps its electrons and doesn't want to form a new a new oxygen nucleophile bond. Okay, and then Dr. Peterson wants us to omit part E. Okay, so is there a question, I think? Let's see, where's the chat box? I gotta pull it up. But for B, would bromine be better because it's less electronegative than fluorine? Let me think about that. Wait a minute. Yeah, I'm getting two conflicting things here based on two different ways I'm thinking about it. And one, you guys see, like, in one way, when you think about it as leaving group stability, you get B. But when you think about it in terms of electronegativity, I get bromine. I meant to say fluorine the first time and then bromine the second time. Interesting. The answer is definitely fluorine. I'm going to go with leaving group ability here. Like, bromine is the more stable on its own. Fluorine is not. So fluorine wants to be attached to the molecule where bromine doesn't need to be. So I'm going to go with what the answers that I have, honestly. I wish I had a better explanation. I'm sorry. And yeah, I can explain D again. Okay, so for D, yeah, so between the heteroatom, which is nitrogen, or the oxygen, the heteroatom here is clearly nitrogen, and it's less electronegative, okay? Which means it doesn't hold on to its electrons as much, which is a good thing. Because if it doesn't hold and it hoard all of its electrons to itself, it can give those electrons to something else and form a bond. And that's the whole point of this nucleophilic substitution thing. And this nucleophile can substitute into the molecule. Whereas this oxygen one wants to hoard and be selfish and keep all of its electrons to itself. Okay. Let's see what's going on here. The keys might be changed. I know this stuff for sure. I told you, this is more abstract. It's not as cookie cut, but I don't think it's terrible. Okay, so let's keep moving. Yeah, let me just jump around now. Okay, so I think we did enough of the basics. Now I kind of want to jump into like the main questions. So let's just go. And I think we should probably touch on a little bit of elimination. I think you guys are kind of due for some of that already. You have been eliminated. Okay, I'm pulling up some questions. Let's see. All right. Yeah, so I think we're there anyway. So I'm just gonna do a few quick examples. I think we practiced this last time of just knowing how to do SN1 versus SN2. Oh, am I sharing still? Okay, gotta stop that so you guys can see. Okay, so essentially, we're just gonna move on to some of these predictive products. So for now, we are just ignoring elimination. I haven't taught you guys about elimination, so we're just going to assume only SN1 or SN2 pathways for now. That is not true. This is not what happens in the real world. But for this problem, just do that, okay? Because I always have people that are like, wait, why? We're just saying that just to help teach you guys along the way. And guys, all of the Orgo 2 classes are gone. That's crazy. I heard that this morning. Like, the fact that there are no seats left, that's crazy. Like, there's so many sections. That means so many of you guys are probably taking it. Oh, now they're back? Oh, okay, maybe there's some more. Okay. Maybe this morning there weren't and they added more. Oh, but no lab. Yeah. Well, even if you, I know a lot of you guys are a little nervous with Bartmus, but like, seriously, he is a really great guy. He's a good professor. He's going to teach you a lot. And you still have all of my YouTube channel. I'm going to send you guys a couple of documents before you guys leave the class, and I'll give you guys some stuff to prep you guys to go in, and we'll all be good. We'll all be good. And I can go over recommendations in a second. All right. So basically what you want to do is the first thing with this is classify the substitution of your starting material, right? So this is a secondary, starting material. And that's the gray area. Remember, we draw this graphic is so important. I love this graphic. And you need to know that there's SN1 going on here, and then there's SN2 going on here, and then there's overlap going on in between. So you have to slow down. Every time you see a primary, SN2, don't think. Every time you see a tertiary, SN1, don't think. But when you're in the secondary region, you have to slow down and you have to ask yourself two more questions. Now the two gray area questions that I say, that quotes gray area, would be the strength of the nucleophile, okay? And then next would be, you know, the type of solvent. So type of solvent. So those are my two questions I have to ask myself, okay? So the first thing is this a strong or a weak solvent? Excuse me, a strong or a weak nucleophile? Strong, right? We have a full negative charge when we dissociate the spectator ion. So strong is one of those conditions for SN2. We've talked about why. And DMSO is a polar protic or polar aprotic? It looks like this. Oops, there should be sulfur there. Looks like that, dimethyl sulfoxide. It's aprotic, great, it's aprotic. So those two pieces of information are going to basically push this secondary down the SN2 pathway. Do you guys see that? Great. So you know it's SN2. So that means that you have to have two arrows in your first step. The nucleophile coming in, which causes the leaving group to break. Remember, SN2, bimolecular. Two things have to happen in the beginning, okay? So the next thing is going to be the product of this, but you guys know sterics. You guys know sterics. I feel like I've been a broken record. So if the dash face is sterically hindered, the back face, what is the stereochemistry of the incoming thiol nucleophile? Boom. You guys got it. All right. So this is very hard to learn. Like, I feel like if someone's not dumbing it down for you, okay? I don't know if you guys feel that way, but I think you guys are feeling a little bit better with how to approach these problems. It's very simple, and when you break it down, okay? Do you guys kind of feel that so far? I hope. I don't know. All right, B. Let's keep going. So let's try another example. So here we have this kind of starting material, okay? And we have, you know, I'm just going to draw CH3OH, okay? Classify the substitution pattern. What is it? Tertiary. No thinking. SN1, okay? I know that SN1, dependent on the leaving group leaving by itself, this forms a carbocation intermediate, okay? And then your main, you know, methanol substituent or nucleophile can come in, form a bond, okay? And you remember, you always assume excess reagent, so, you know, that reagent can just come in and depronate, and you synthesize an ether, okay? And it's not chiral because of, you know, not a chiral center there. Okay, so that's B, all right? I'm just gonna do another example. So let's just do, this is H, I'm just jumping around. So I don't wanna do all of them for you so that you guys can have some time. H looks like this, so chlorine and NaN3 and DMF. So essentially, secondary, slow down, gray area, okay, we don't know. Ask myself those two questions, strong or weak, okay? This is a strong nucleophile because it's the azide. This is the bullet. Remember, this is the bullet example that we used. Okay, so strong, aprotic, okay? Again, forcing me down the SN2 pathway. So I'm thinking azide's gonna come in and kick off the chlorine. Remember, the wedge face was, you know, sterically hindered. So the azide comes in on the back face. So something to note, with SN1 pathways, you typically get racemic mixtures. But with SN2 pathways, you typically get one singular enantiomer. And specifically, it's the opposite configuration of your starting material. So let's just like look at an example for I, and we have kind of this benzylic bromide. And essentially you have this example. So this is kind of something that tricks people up. So yes, for SN1 conditions, you have racemization, so racemic mixture is forming typically. With SN2 pathways, you typically exclusively get one enantiomer, and specifically that enantiomer is the opposite configuration of your starting materials configuration. Yep, yes. Okay, so essentially here we have, you know, this primary. This primary tells me to think SN2, okay? So then you see that, okay, this is a relatively, and I'm saying this relatively as important, it's strong because it has a negative charge, okay? So we can say it's strong. Okay, but this is weird. What's the solvent? What's the solvent? Protic or aprotic? Protic, right? So that's weird, right? So do you guys have alarm bells going off? A little bit, some people. Essentially, you guys are right. This is an SN2 pathway, okay? So something I just want to point out to you guys. So it's one of those things that you kind of just have to accept. whenever you have alkoxide nucleophiles, what an alkoxide is, it's just an alcohol that's been deprotonated. Okay, that's where that comes from. So an alcohol, so like let's just say something like that, that's the alcohol, okay? And then when you deprotonate it, so base or something like that, base, you get this anion. So that's the alkoxide anion, okay? So that's important. Specifically, whenever we have these types of nucleophiles, the solvent, just because this is how they're manufactured, it's typically sold, this main reagent, in its protonated version, okay? But they play with the acidity of the solution to make sure that you have more of this than that. Does that make sense? Kind of, sort of? So regardless, it's still SN2, even though it's aprotic, it should be aprotic conditions. The only time, I'm telling you, this is the only time you see this, is when you have these alkoxide nucleophiles. They're typically dissolved in their protonated solvents instead of an aprotic solvent, but it still goes under the SN2 pathway. This is the only time that you guys see this. Yes, as well. Okay, but Leah, you could also have a situation where there'd be no reaction possible because all of the reagents and starting materials don't align. So I don't want to say always, but yes, good idea to always think that that would be a good area to start or look towards. Okay, we're getting close to the end of the time here, so I think that's kind of good for how to approach these predict the product questions. And the reason why I'm not going to do all of these is because this isn't really what we would have you do on the test because you haven't learned elimination yet. So this is just a great way to practice how, up to this point, do you know SN1 versus SN2? Do you know the little ins and outs? Do you know how to rank? Do you know what the solvent does, what the nucleophile does, all those things? Oh, the product, sorry. Yeah, so this is going to be SN2. So essentially the charge goes in here, kicks off the bromine. So you get a really long molecule now. It's an ether where you have, oh, sorry, there should be one more carbon. So yeah, it should be, oh, I did it again. Okay, hold on. Oh, it's been a day. And then how many carbons? 1, 2, 3. 1, 2, 3. Boom. Yeah, you heard David in there? Did you hear a little bit of David? I love that show. You guys should all watch it if you don't. It's like it's 20 minutes each episode, and it's one of the few shows that actually makes me laugh out loud. Like, seriously, I love it. Anyway, let me just look through the workbook real quick, see if there's any more problems. I think somebody requested 7. I'll do one example of 7, and then I think we'll be good for the day. Okay, and then, yeah, we'll be literally just at elimination. That's perfect. Cool. I'm happy with that. Oh my God. Go us. We did a great job. Okay, 7A. It's called, here, I'll put in the chat box. It's called Schitt's Creek, but it's spelled like normally. Yeah, there you go. Not normally. There you go. Okay, so an A. Okay, so funny. You guys would love it. Seriously, I think everybody should watch it. So what you guys learned today was not organic chemistry, but Steven's favorite TV show. Okay, so essentially, what this question is really just saying is, it's like, do you understand that all these pathways are SN1 conditions, and but as such, they go through carbocation intermediates, which then later rearrange, right? So since it's SN1 conditions, we get this, you know, basically secondary carbocation. And what happens is that you're going to cut here. And then what happens is that this bond is going to form there. So, you know, you get that whole ring expansion situation going on. And I'm not going to go into the details of a ring expansion. You might have to go a little bit slower. But essentially, you can see that you're going to form a ring that looks like this. So that would be your first product. And then after subsequent, you know, rounds of the nucleophile adding in and, you know, deprotonating, you would get, you know, your final product where that methoxy group comes in. So that's kind of the logic. It's like you rationalize that you're going to form a carbocation, and every single one of these examples you're showing potential rearrangements. So that's kind of the goal of this problem. So you have to just know that when you do these SN1 conditions, it's yet another example of a carbocation intermediate, which means you always have to check for rearrangements because this is your end product. You know, you have to remember that all those old chemical, you know, laws still apply, right? With that, I think we did a lot of practice. What we're probably going to do is on Wednesday, we'll just finish up with, we'll introduce and probably finish beta elimination, and then you'll be done with the chapter, which is great. Beta elimination, people don't really like E2, but we'll figure it out. And the other thing I wanted to say is what we're going to do is I'm going to send you guys a document next week when we get back, and it's going to be like a huge like packet of just a whole bunch of these problems, and you have to know like which one's E1, which one's SN1, which one's E2, which one's SN1 and E1, things like that. So I think the only way to do that is to see like a whole document of problems mixed up together and you just get good with it. So I have that already made. I'll just send that out to you guys next week. And Wednesday we'll probably, I might modify the time. I'm seeing my grandpa when I go home, so I don't know. I'll let you guys know when I know. All right.
Stephen?
Yeah,
I have.
Here, Mike.
Can you hear me?
Yeah, I can hear you. What's up?
Perfect. So I just have a proposal or not. You can take it or not. Like, do you remember how not back in the day, but we were doing the reactions. We made that little what was it? The paper stuff. Like we made.
Oh yeah, the squares.
Yeah, the squares. I was wondering if we could do the same thing, but for SN1, SN2, E1, and E2, if possible.
Yeah, 100%.
Thank you.
I think we should just do it though when we do E1 and E2. So maybe we'll do it either at the end of Wednesday or we can do it at the beginning of next week. Is that okay?
Yeah, that's perfect. Thank you.
Well, yeah, I'll definitely do an exam review for this. So yeah, so we'll do that. All right. See you guys. Happy Wednesday or Monday. Sorry. Bye.